Thank you, Michael. I'm very glad to be here to talk about this. I'd like to acknowledge a number of people, particularly Larry Calderon and Dan Blumenthal, who I collaborate closely with, and then a number of students who do most of the work, and a number of companies, Intel in particular, as well as Orion, located in Santa Barbara, and Hewlett-Packard. So, as Mike said, there's 6 areas of the Institute, and the talks this afternoon will primarily focus on 2. Electronics, photonics, and computing, in terms of the work that I'll describe, and then a supercomputing section that comes next. The problem we're addressing is that the internet is growing very quickly, right, doubling every 18 months, and this requires increasing amounts of power. So the solution we're going to talk about is using photonics to communicate that data across data centers, across supercomputers, across the world, and talk in particular about doing this on silicon as a low-cost way to do this. And look at the impact on supercomputers and data centers, and we'll hear much more about that later in the afternoon. So that's kind of an overview of what I want to talk about. This slide from Intel talks about all the data that's being generated. We've all seen this from Google Earth and the ability to look at your house and everything else. There's increasing amounts of data becoming available. You know, a zettabyte's a lot of data. It's 2 to the 70th power, right? That's where we're at now. And so I think Bill talked about exascale computing, exabytes. A zeta is 1,000 of those, 10 to the 21. And that's a lot of data being generated, and it's all typically stored somewhere in a cloud, and that needs to be communicated to all of us to become useful. And so as a consequence, the traffic is growing very rapidly. A number that people often use is 2 dB per year, which means in 5 years, that's 10 dB. That's 10 times the traffic you had before. So every 5 years, you have to have 10 times that communication capability. And the problem is if it takes the same amount of power, then you're really in a problem, right? Because in 5 years, the internet will take 10 times the power it does today. So maybe it's 4% today. That's 40% in 5 years. And at the end, a decade from now, that's 440, more than a factor of 2 higher. So that's the point. 10 years is 20 dB is 100 times. And if you look at what the causes of that are, this is a Cisco study. It's changing. There's a lot of different aspects to it. You probably can't see it, but it's video on demand and things like this. And increasingly now, where we're moving to is basically internet video to your home or to your PC. And so there isn't any indication that this is slowing down, but will continue for quite a long time. Photonics, in response to that, has been growing its capability. So the first photonic transmission systems were back about 1980. Kind of somewhere below the floor here at about 50 megabit per second. And more recently, there have been a whole series of inventions that have gone on. And so we're now basically up to sort of 10 terabits or maybe 20 or 30 terabits. And the belief is that will continue to expand. So we will be able to provide that information. The question is, can we do it cost effectively and power efficiently? If it takes 10 times as much power, or 10 times as much money, we're definitely in trouble. So today, most of us on our computers have 10 gigabit connections. Routers these days are just moving to 100 gigabit connections on the front face of all of those. And the belief is that in 5, 10 years will move to a terabit. And so one issue is how do you get to this terabit optical Ethernet? And there's a bunch of ways that will happen. Part of it's by signaling at ever higher speeds. As silicon gets faster, then clock speeds will get faster. So today, 5, 10 gigahertz is common. We'll move to 25 fairly soon, and probably beyond that in the future. Part of it is by having ever more colors of light traveling down the fiber. So this is called coarse WDM. So this is what's common in very inexpensive systems where they don't have any temperature control, but 6 or 8 wavelengths of light. Way out here, one gets to typical systems for long haul are perhaps 100 or maybe 200 colors of light. Again, that way you can take, say, 10 gigabit with 100 colors, gets you to a terabit per second. The other big area of research is more complex modulation formats. So just like your cell phone has, some high level of modulation format to get lots of bits per hertz. So the transmission spectrum over cell phone towers is very limited. So already they have gone to more complex modulation scheme. For the most part, optics today is back here. 99.9% of all optics is just on-off. Just turn the light on and off, basically, and that's it. But increasingly, these very complex modulation schemes, like we have in cell phones, are what will happen in photonics. So the capability is there to do it, but typically these complex modulation schemes are very expensive and they take a lot of power. So those are the issues we have to work on. The other thing which is happening these days, and this is a very hot topic in the research conferences, is this line of space division multiplexing. So today, down an optical fiber, you have one beam traveling down it, perhaps many colors of light. But the focus now is to get typically 7 beams of light down a fiber. So there'll be 6 around the outside, 1 down the center. And again, that just means at the end of that fiber, you've got a very complex receiver that now has 7 times as many things on it as you used to have. So the general point of all this is photonics is getting very complex, lots of parts. And so there have been efforts to integrate. This is, frankly, where today most of the industry is still at. Every time you have a different color of light on that fiber, there's a separate laser for it. There's a wavelength blocker for it. There's a modulator. There's perhaps backface detectors. And then all these get combined in a single wavelength combiner. And where that's moving towards, integrating all those components on a chip. That's absolutely essential, because this is really expensive, right? All these have devices in a package with a fiber coupled to it. And you add all that up, and you've got 40 or 50 fiber connections, and each of them with a separate power supply and electronic connection, things like that. This is really where the world's going. But this is really not very much, right? This is 100 gigabit per second. That's very primitive compared to most of what I just talked about in the previous slide. So there is a lot of research at UCSB going on in this area. There's a center that Larry Calderon runs called PICO for Photonic Integration for Coherent Optics. So its goal is to make things like these complicated receivers that do coherent demodulation of signals or transmission of signals. And there's other sorts of photonic crystals and a whole roadmap of where that center is going. There's another center, the Terabit Optical Ethernet Center, that Dan Blumenthal runs and was announced about 9 months ago. And again, you've seen this chart already in terms of how do we expand capability. And that's with many colors of light, many wavelengths, hundreds of wavelengths. The single wavelength approach is down here, and the roadmap that Dan is advocating is here. And within 10 years, the goal is on a single color to get a terabit of data. And then if you have 100 colors of light, you have 100 terabits going down that fiber. And so it's drawn down here as a cartoon, but of a fairly complex optical circuit that will accomplish all of that, coupled to a very complex field of size circuit that does all the control and reading of data. So that's another big effort at UCSB. As a result of this integration of parts, this is kind of where we stand today. So, pretty much back in the early 80s, back sort of a gigabit per second data transmission, there was typically one device in a package, one laser. And increasingly in research, we've gone up to levels like this, and this is work out of Dan Blumenthal and Larry Calderon's group, this motor chip that is shown there on the top. And that is state of the art, 300 elements linked together. So that's good, but that's, again, not where we need to be in 5 or 10 years. So our whole group effort now is to make something much more complex than that. And a lot of our focus in the Institute is doing this on silicon. And there's a very rich, strong process technology in silicon that goes way beyond, orders of magnitude beyond where photonics industry is. So today, there's 7 billion transistors on a chip. That's very high yield, very high levels of integration. We want to apply that to the photonics industry. And so here's one viewpoint. This happens to be an IBM slide of what they're looking at for supercomputing. And the idea is you've got a plane of processor chips. So you've got hundreds of processors, hundreds of cores on a chip. And that's bonded to a memory plane. So again, the advantage of that is that the delays between memory and the processor are now very short. And you might have multiple memory planes to get sufficient memory close to that. And then you have a photonics plane on that. So these are all just chips bonded on top of each other. And these different cores, these are supposed to, these black squares represent different cores in this processor, are then all connected optically. And the reason they're connected optically is that you've got 200 data lines at a 5 gigahertz rate. That's a terabit per second going from each of those cores. So on that chip, you're going to have something like 500 terabits of transmission That's not unlike sort of a national sort of level today integrated onto a chip. And the goal is this will happen long before we get to exascale computing. So it's something that has to happen within the next 10 years. So we'd like to do this. The problem with this is that silicon is indirect band gap. It inherently doesn't emit light. If you forward bias the p-n junction, it gives out heat, phonons, rather than light. Second problem is because it's indirect gap, it's a really lousy absorber. People don't make detectors out of silicon today. Silicon is centrosymmetric, which means it's a lousy modulator. These are all the reasons that the photonic industry is based on indium phosphide and gallium arsenide. They don't have all of these problems. There's SiO2 layered SOI wafers. That's resistive. That's a problem. And then finally, silicon is reciprocal, which means that it transmits inherently the same both directions. And most photonic devices need isolators. And so they need a non-reciprocal element. So that's the problem. That's what we're trying to address in this. If we are successful, then what we can do, though, is combine all the laser technology we've seen, do it in a silicon CMOS foundry with all the complexities and capabilities of CMOS, and end up with something that takes us many generations forward. So photonic integrated circuits today are on these sorts of sizes. They're probably too low to see, but fairly small wafers, 2 or 3 inch diameter wafers, fairly coarse levels of lithography. And if we can make all these photonic devices we just shown on silicon, we can directly move to a modern silicon CMOS foundry and jump literally 6 generations of technology. And that's our goal. That's what we're trying to do. The approach that we have pioneered in the Institute is to put layers of 3-5 materials. So these 3-5 materials are direct band gap, they're efficient light emitters, they're efficient detectors, they're efficient modulators, and put them directly on silicon substrates and then run them through a CMOS foundry. And the 2 partners we work with in this, or 3, actually all 3, but in particular Intel and Orion, run these parts through conventional CMOS foundries today. You can make a lot of different devices. This happens to be one particular device, what's called a distributed feedback laser. The point being that when you look at the light emission out of it, it only emits at one very particular, very well-defined narrow wavelength. And that's critical because we want to combine hundreds of these together. And each one has to be very precisely positioned. And again, because the gratings that determine that wavelength, these little dots right here, are very precisely determined in a CMOS foundry, we can hit those levels of control. This is one of the chips that one of my students made, Siddharth Jain. But the point of it is that we're now at the point where we combine 16 different wavelengths together on one chip. Or in that case over there, 16 wavelengths with 16 modulators and detectors. So again, not huge amounts of integration, right? You know, on the order of 60 elements on a device. But we'll get in a second to where we want to go. And the point being that we can now get 16 colors of light. And the next issue is, can we modulate those fast enough to get to these sorts of terabit speeds? The other issue, this is a conference on energy efficiency, but in particular for supercomputing, Bill Brinkman mentioned the problem of, we can't have gigawatts of power in our exascale computer. The connectivity has to be very low power. And so today our threshold currents are up here at say 50 or 60 milliamps. And we're now looking at how do you get down to sub-milliamp. And we've gotten fairly close to that, about 2 milliamps. We're trying to get lower. But in particular, there's certain types of lasers. These are ring lasers. And this is a wafer with literally something like 1 million ring lasers on it. And the point being, the number that I want you to remember for a second now is if we operate this at 10 milliamps at 1 volt, that takes 10 milliwatts. And if we operate that at 25 gigabit, which is the next standard, after 10 gigabit in a data center will be 25 gigabit, that requires about 0.4 picojoule per bit. So remember that number. We have to get lower than ultimately, but to break in, we need to hit 0.4 picojoule per bit. So that's 2 elements of it, lots of wavelengths, low power. The other wavelength is, can we make fast modulators? So again, this is a silicon wafer, and the point being it runs at 50 gigabit per second. So where we're going to head with this is 50 gigabit times 20 wavelengths is a terabit. So we're not too far away from being able to get there with this technology. This is some work out of Intel. So they had a press release on this last summer. Justin Ratner is the CTO at Intel. And they discussed a 50 gigabit per second link, which is processed in a CMOS foundry. It uses a lot of these same ideas. So there's In this case, there's 4 colors of light, 4 hybrid silicon lasers. There's 4 modulators. They combine it together. It's all in one chip. And they can make this in a CMOS foundry and make it very low cost. Mario Panicia, who runs this effort, his whole thing is this has to cost $1, right? He has to put this on a laptop and make it cost effective. The question is, where do you go from there? And so that's where this is now, 12 gigabit per second, 4 wavelengths, 50 gigabit. We now want to get to, say, 25 gigabit, 16 wavelengths, or maybe 40 wavelengths, then we get to a terabit. And so that's kind of where it's going, and we've got the elements to get there. There are a lot of other devices one needs, and we work on all those other elements. These are all things we've demonstrated that one needs to make a real optical system. I want to talk about, just briefly, just to close up, a few things that tie into later talks in this session. But there's a big problem with making routers. And a modern Cisco CRS1 router, if you fully put it out, takes something like 1 megawatt of power for just that one router. There's an effort at UCSB on what's called the Laser Project to build an all-optical router. And it's in collaboration with Cisco. And Dan Blumenthal runs it. And here's some of the chips that are being made in it. But again, they all require lots of integration of lots of optical elements together. And the goal is to make something that takes a small fraction of that megawatt of power, or equivalently takes a megawatt of power to handle 100 or 1,000 times as much data. There's another project at UCSB called IFOD, and the goal is to now reduce the losses, optical losses on fibers. And those are working really quite well. The losses today are literally 50 times lower than silicon. It's on a silicon wafer, but it's a different wafer technology. And you can make very high Q resonators, literally Qs of 18 million on a chip, which is unprecedented. In terms of data centers, there is this push. Data centers are now looking at 100 gigabit interfaces, but 100 gigabit switching devices don't exist yet. Theoretically, optically, you can do much better. This is power, again, in, well, it's nanojoules per bit, but so this is a picojoule per bit. But optically, you can switch data with a lot less power than electrical. And that's inherent, because electrically, you look at every bit. You process every bit in a computer. Optically, it just flows through. You just sort of switching a stream around one way or the other. And inherently, it's lower power. In terms of high-performance computing, we'll hear a lot more about that today. This is one example of one of the IBM systems. And the point being that there are fibers on these today. So these are all optical fibers running in. So they're running in close to chips. But increasingly, they're going to move onto chips. And that's the real drive to put photonics on silicon, is to make all that just much denser. One of the big ways that's being done today is with vertical cavity lasers. That's probably the dominant technology in a data center today. And Larry Calderon's working extensively on this. And they got some of the best results in the world at 25 and 35 gigabits per VCSEL. And they have ideas for how do you move further, perhaps 50 or 100 gigabits per second. And so that's another important effort of what's going on at UCSB. This is an old slide. This is actually 10 years old, but I wanted to bring it up. It's Steve Wallach, who started a couple supercomputer companies, Convex being one of them, Convey being the other. And his idea is that, again, you use optical switches to combine racks of supercomputing elements together and use the fact that these switches are very low power. And so that's one person's vision of where the world's going. If you can get these very low power levels, and I mentioned 0.4 picojoule per bit is where we're basically at today, you can save a lot of power. So these are all the world's supercomputers, or at least the top 10 or 15 computers. Here's the 2 petaflop number. And so higher throughput is up here. Bill mentioned we want to get, obviously, to exascale. So you want to go 50 times above this, or 10 times, 100 times above that level. And what's going this way is power is this way. So this is bad over here. Goodness is over there. And so here's all these different computers that all fit on a straight line. The point of this curve is this. If we can reduce the power of optically interconnecting these supercomputers to on the order of a picojoule per bit, it's this line right here, then we can save a factor of 100 in the power of that supercomputer. So that's the goal. We need to make very high radix, very high port count, very high speed, but very low power. So we can hit a picojoule per bit. We can probably hit it 100 femtojoules per bit. And then you're actually talking about another factor of 10 below. So then you really can go from 2 petaflops to 2 exaflops and have the same power in terms of interconnecting those. So to summarize, I've talked about things that photonics can do, lower power, more efficient ways to communicate. Today, it's ubiquitous at a wide area, even a local area, right? We now increasingly have fibers going to our home. That's going to keep getting closer and closer within data centers, onto chips, and within supercomputers. These complex ways of getting more data onto a chip require lots of elements. And so integration becomes absolutely essential for size, weight, power, and making it very inexpensive. And personally, I think doing things in a CMOS foundry in a hybrid silicon way is the way to get that process technology. So thank you.